In this video, I'm going to explain how to do the calculations for the pH titration curve experiment. Alright, so the first thing that you did was you titrated some KHP. The purpose of those titrations was to find the concentration of your sodium hydroxide solution. And so KHP is a monoprotic weak acid. Sodium hydroxide is monobasic, and so it's a 1-to-1 mole ratio between sodium hydroxide and KHP. And so what that means is that at the equivalence point, the point at which you'll have added the same number of moles of sodium hydroxide as there were KHP in your beaker, moles of sodium hydroxide is equal to the moles of KHP. Well, you can calculate the moles of KHP. It's just however much you weighed out, the grams of KHP divided by its molar mass, which I gave you as 204.22 grams per mole. So the number that goes up here, it's whatever you weighed out. It's probably between 0.4 and 0.5 grams or so. Once you know moles of KHP, you know moles of sodium hydroxide at the equivalence point. So to get the concentration of sodium hydroxide, all you do is take that number of moles, which is the same at the equivalence point, it's the same as the moles of the KHP you put in there, which you calculated this way, and then you divide by the liters of sodium hydroxide at the solution. So you found the equivalence point on your titration curve, and you read the pH and the volume of sodium hydroxide solution added in milliliters. So just convert it to liters, put it in the denominator here, the moles that you calculated up here on top, and that's your concentration of sodium hydroxide. Now you did 3 trials, so take the average of the 3, and that number there, once you take the average concentration of sodium hydroxide, you're going to use that concentration for the rest of the experiment for the calculations. So you did 3 acids, a monoprotic strong acid, a monoprotic weak acid, and a diprotic weak acid. For all 3, the way to find the concentration or the molarity of that acid is, it's the definition of concentration or molarity is moles divided by liters of solution. And for all 3, what you did is you pipetted 10.00 milliliters, which is 0.01000 sig figs liters. So that's the volume for all of these calculations here. The moles of the acid, the first 2 acids anyway, were monoprotic, and so we know the moles of the acid is equal to moles of sodium hydroxide added at the equivalence point. And so if you know this, which goes here, right? Well, to get this, because you now know the concentration of your sodium hydroxide, it's whatever your average was from just before. Just take the concentration, the moles per liter, times the liters that you added at the equivalence point. So just like before, you found the pH and the volume of sodium hydroxide solution added at the equivalence point. That was milliliters converted to liters, multiplied by your average concentration of sodium hydroxide. And that's the moles of sodium hydroxide at the equivalence point, which is equal to the moles of the acid, which goes up here. You divide by 0.01000 liters, and that's the concentration of your acid. Now for your diprotic acid, you only have to do the first equivalence point to get the concentration, but if you'd like, you can also do the second equivalence point. The only difference there is that for the weak diprotic acid, you will have not a 1-to-1 mole ratio, but a 1-to-2 mole ratio. So this is only for the diprotic acid at the second equivalence point. And you don't really have to do that. It's a good check to see. You should get pretty close to the same thing you got from the first equivalence point. All right, so those are the concentrations or the molarities of the acids. Now to get the Kas, it's really easy because for all of your acids, the weak acids, monoprotic and diprotic, you found not only the pH and volume of sodium hydroxide solution added at the equivalence point, but you also, if you remember, found the pH at halfway to the equivalence point. Thinking about the HendersonHasselbalch equation, which is what we're using here, pH equals pKa plus log of the base over the acid form. At halfway to the equivalence point, the concentration of the base form is equal to the concentration of the acid form of this weak acid. And when this is equal to this value here, this ratio is 1, log of 1 is 0, and so pH is equal to pKa. So you read the pH at halfway to the equivalence point. That is the pKa for that acid. Ka will be 10 to the minus pKa. Now for your diprotic acid, it has 2 Kas. The first one, do just like the weak monoprotic. For the second one, what you found halfway from the first equivalence point to the second equivalence point, the pH there, that is equal to pKa2 for the diprotic, and do the same thing. That's all there is to it.